Hi, I'm Nikita, and I will tell you today about my work on contextual model types for algebraic effects and handlers, which is a joint work with my advisor Alex Nanevsky. Algebraic effects are those effects in programming and programming languages that are defined by a set of operations that your programs might call. For example, we can model an effect of a single cell integer state with two operations. One is get, to read an integer from that state, and one is set, to write a new integer into that. With these operations, we might write a program that, for example, increments the state, and it does so by first reading the current state value with get into x, and then later by setting a new state value, which is x plus 1, to our integer cell. And then it returns the previous state value. This previous state value is integer, and we type the program as integer. But moreover, what we typically want to know in programs that use algebraic effects is which operations they used. So we track their effects also in the typing alongside with the return type of integer. And we call such type systems that also track operations type and effect systems. And let's look closer at this type and effect system annotation. Those annotations actually and type and effect systems in general are currently an active area of research. There is a lot of papers published right now about type systems for algebraic effects. One common feature among them, though, is that all of them are treating effect information as a second-class citizen in the typing system, meaning that there is no direct way, no direct term in the language to add or remove or introduce or eliminate these effect annotations. They are collected implicitly from the term in a bottom-up fashion. In practice, this summer, people that made algebraic effects for OCaml published a paper about it. And in there, they also considered, well, what is the best type and effect system that we can choose right now for OCaml? But they noticed that actually they cannot choose yet an effect type and effect system for OCaml to track their algebraic effects, because there is not yet a type and effect system that would guarantee you the essential property of effect systems, that is effect safety. All your effects, if your type system tells you that there is no effect, then it's true. And effect safety is not something that current systems can guarantee yet in the presence of advanced features such as polymorphism, modularity, or generativity. And it is our idea that it is exactly because current type and effect systems treat effect annotations as second-class citizens and don't have terms to manipulate them in the language that this problem arises. So what we think is missing is exactly this ability to manipulate effect annotations directly. And so our idea is to move from a traditional type and effect annotation into a purely typing system and use something called a contextual model box type. It is a generalization of a simple box type that you might know from model logic, from linear temporal logic, which is also called necessity type, for example. And it is generalized by a variable context, where for us, actually, effect operations are variables. Note that it is not just a change of annotation. We actually change the language. We introduce constructors and destructors for this type, which also manipulate the effect annotation. We formalize our work in the system called ECMTT, which is an extension of contextual model type theory with algebraic effects. So what does it actually bring us to use model types? First of all, our typing system starts to manipulate effect annotations directly with introduction and elimination forms for effect scoping. Our operations become just bound variables in terms, and we can, for example, alpha rename them. And moreover, our operational semantics becomes super simple. Instead of many rules how to define handlers on your computations, we have just one, but I will show you. And the main insight that we obtained in doing this work that I want to communicate with you right now is that contextual model typing is actually the logic behind handling of algebraic effects. That was our big discovery. But let me go into detail and show you the language. So we have this model box type, and it is a box type generalized by a context. We call it psi in the slide. And the term to introduce this type is called also box, that now explicitly binds this context psi. For example, remember the Tinker program. Now, to make it into a box type, we say box get set, and then we repeat the Tinker program. By this way, we construct the model type. Note that this box must actually bind the full signature of effects. There is, if we say get and set, there is no other effect that we can use in that program. But let me show you. For example, if instead of a set we used raise, which is supposedly raising an exception, then our typing system would rule this program out, because raise is not under the box. Alright, but how do we actually use this type? And here is the elimination for it. It is a let form, and it works by binding the box type to a variable, a term of a box type, and then using this variable in another term. Note that it is just a variable rule, essentially. It gives you a variable. And it is actually very crucial for our semantics, because it is the only beta reduction that we have in our semantics. It is just beta reduction. It works by, well, reducing the box term to an actual box, taking the computation out of it, and substituting it for the variable. The way to use that variable is actually with handling. That's where handling comes into play. So handling for us is a variable rule. It applies not to a computation, but to a variable, and it is important because it allows us to keep the operational semantics simple. We don't have to define handlers on every clause of a computation. But let me show you an example of how handling works. So remember the Tinker program, we put a box around it, so it becomes a box term of a box type. We eliminate it with letBox. We bind it to a variable u. Next thing we do is we apply handling to it. We use some handler for state and on that variable. Remember that the only beta reduction that we have is the letBox contraction, so that's the only thing we can do in this program. We cannot reduce handling right away. Let's do it. So the way the reduction works is that we take this computation of Tinker from under the box, and then we substitute it for the variable in the handling term. Handling then is defined as just a meta operation during a substitution. It's not a standalone thing. And we reduce it accordingly. We do the substitution, and it's a meta operation. And then it runs as defined by handler st, as you would expect. It all happens during a single beta reduction step. There is no separate reduction for handler. So what I showed you before was what we call local soundness, that we can distract our constructor or eliminate an introduction form, and we are in balance. Another side of that balance is local completeness or entity expansion, that we can take our term of a box type and expand it into a regex. We expand it into a letBox that binds it and then reboxes it and handles it. But here we use a very special handler, which we call identity handler. What it does, it explicitly propagates the effects from one effect context psi to itself. So, for example, if it was state, then what we would do is we would say that get maps to get and set maps to set. And it is very important for us because actually we can not implicitly leak effects otherwise. We must explicitly say how operations from the inside, one theory, map to another, to the outside. And that's where identity handlers come into play. And together, those two properties of local completeness and local soundness actually ensure that our design for our type of effect is modular and it is independent of other language features. So let me conclude for now and talk about what we actually achieved in this work. So we found out that contextual model typing is a natural fit for systems with algebraic effects, that it naturally describes handling, that handling is a manipulation with contextual model types. Contextual model types provide for us a direct control over effect scopes and effect annotations. They connect algebraic effects to model logic, which potentially allows us to transfer the results between the two fields. And let me give you an example of it right away. So currently there is a lot of research into effect polymorphism, which is a polymorphism over effect theories. And in the slide, we show you an example that we adapted from a paper from the Popol 2019 that shows a problem with accidental handling of algebraic effects. We stated it in terms of model type systems, and we actually want to adopt a solution from model type systems because 10 years ago, Brigitte Pientka wrote a paper that wasn't about algebraic effects at all. It was about contextual model types. But we think that it was exactly the problem that currently algebraic effects researchers are solving. And we want to borrow that solution, and we think that it will be immediate solution to the problem of effect polymorphism, because for us it is a context polymorphism, but it had already been worked out. And you will find more details on that example in the paper. Another thing that we want to do is we want to develop Kripke semantics for our model effect types, which we will see entirely as propositions. We will switch from a language with terms to a language of only propositions that are standing for our effect types. So in a way, what we will get is we will consider the system of a logic for manipulating algebraic effects. We will replace our term judgments with judgments of validity, possibility, or truth, and we plan to develop Kripke semantics for it, which is something that is traditionally done for systems of model types or model logic. And by that, we will obtain immediately a Curry-Howard isomorphism between programming languages with algebraic effects and systems of model logic. But that's a future work. One more thing that we want to do in the future is to look into our equational theory. Because for us, right now, this modality of box psi behaves both as a monad and a comonad, which is peculiar, and we want to explore it. And the next big thing is dependent types. We think that we will have a good shot to getting to dependent types because, first of all, the work we base on, SymTT, was already lifted to dependent types, and its development also. Moreover, we have enough features of the language that are simple, for example, simple operational semantics that will also simplify the lifting for us. And having dependent types will allow us to have equations between operations, which will describe how operations interact and will give us algebraic theories in our types instead of just signatures of operations. And that is it for me. Thank you.